Wes, well, it's good to see you, man. How you been dealing with all this stuff?
Here's your guys' first-hand glimpse introduction to what doing time's all about.
Yeah. Been staying in shape and stuff?
Buff, if it ain't veins, it's fat. If there's no veins, it's fat.
Yeah, hey, but I don't have too long. I've got a Kalman filter lesson coming up.
That is gold.
What is it you used to always say about the Kalman filter stuff?
I only push the hard way because that's the way that works without fail.
Yeah, that's it. Hey, well, if you're not doing anything, feel free to join us, see if you got anything to add during the class.
Well, hello everybody, here we are again, one of the last couple of lessons, plenty of work left to do this semester, mostly programming, but as far as derivations and stuff, we're kind of in the home stretch. All right, I guess from today it's 2 weeks until the LSDC project is due, so it sounds like a long time, but we're expecting a good product on that, so keep that on your list for sure.
I'm getting the chills now. So then I must deliver. We must deliver. You have to have the result they want.
And you might want to reference, I put a new handout in our files section that basically has the PowerPoint slide a little bit more rigorously out, but all the questions overlap, so you might want to use that as your note taker. So remember, our big goal here with the whole Kalman filter thing is to update each new observation without starting all over. That's one goal. Now, we were able to do that with the sequential batch previously, but we also want a solution that's not necessarily pinned to some epoch that might have been 3 years ago. That's the big thing here. All right, now backing up even further, some tools from LSDC that we're going to continue to use is this guy here, right? We use the A's, weights, and B, the error matrix, the B tilde, to figure out a correction that we need to make to our current guess at the state matrix. Okay, so I guess the reason I put this up is we're not coming up with some whole new way of doing it. It is a new way of doing it. Kalman filter is different, but it's still a least squares optimization. Okay, so fundamentally we're still starting with this here. Okay, the problems with it, you see, is we can't just start applying it directly, because that state correction that we get is how you correct the epoch state, and you just stay in that epoch world trying to get trajectories that match the data. Also, the A matrix, that was the partial of how an observation how rho at an observation changes when you tweak the epoch solution that you're using, and so that's not what we want either. So an example, you should be pretty familiar with this by now after all of your coding, but maybe I want to see how rho at observation 5 changes when I change r sub y at epoch. All right, but that's not going to work anymore for us. That's the big gotcha here. All right, some other tools that we already have. With the sequential batch, we figured out that we could recalculate using new data without going back to the beginning. Right, so we have our new correction as a function of all the old material that we've already calculated, and then we put in some little teeny bit of new stuff. And that was just, there was no big astro breakthroughs there. That was a matter of that partition matrix stuff and rearranging it. And it makes sense because you know that you're just building that A and you're building the B, and if you have another observation, they just get tacked onto the bottom. So it turns out if we've done all the calculations up here, we can just keep that in the covariance matrix there and just tack a little something on the bottom. And so we're going to be using that. That's still what we're working towards. The same basic underlying least squares additive process, but with the new stuff that I talked about before, the new capabilities. Okay, so let's see. Connor, you hanging in there?
Give everything you got, all of it, all of it.
All right. So this is kind of the equation we want, but all this yellow stuff and some other stuff, I didn't highlight everything there, but almost everything has to be shifted to the time that we're talking about. If I want to make an observation 6 right now, and I want to know my solution right now, everything's got to be shifted to observation 6. We've got to get away from that epoch. So, to do that, we have to predict a reference trajectory at epoch 6, at observation 6 instead of epoch 6. We can do that. We've been doing that for a while. We have to be able to take a state correction, del x hat, and instead of always applying at epoch, we have to be able to propagate that prediction into the future sometime. And we have to be able to do the same with the covariance matrix. So that's our prediction phase. And then we have to be able to correct it using basically those same linear algebra equations, and then go from there. So we really want to stress that this operation, for us to understand this, it's to predict, correct. Then you get a new observation, predict, correct. And so you really want to pay attention to this. You're not going to be able to track this at all if you don't get the notation down. So Alex, you still with me? If you were fading off, then definitely take a look at this.
I can tell he doesn't want anything you got to give, bro. And that's the point. That's the sad result. That's the hard truth, people.
The bar is going to be a prediction, and then once I correct it and I get my final states and corrections and covariance, it's going to have a little hat above it. All right, so we use cowl to knock out that first part of being able to predict a state at any given time. The next part of it, predicting a del x hat, is what we worked through last time. And so we figured out that we can predict, see the bar there, predict a correction based on a known correction through a state transformation matrix. And then with some Taylor series expansion, first order, we found it was that. And then to find f, we need that. All right, and then this arrow here is kind of pointing, this was kind of your EPs or whatever. There's a lot of zeros and ones in here, which is great. And then there's this little 3x3 corner where you have to find the partial of acceleration with respect to position for each component. So 3x3, I did one of them for you. You're just differentiating, just differentiating the two-body equation of motion with respect to positions. All right, and as always, if there's any systematic issues with the video or sound, I don't have a studio, but give me some feedback if something's wrong every time with these. Wes, what is it you used to say about the loudest man in the room or something?
Saying, oh, the loudest man in the room is the weakest man in the room. What room you in? You ain't in my room.
Yeah, that was it. Okay, so that was where we left off. Now it is time to predict P. Be able to take an established covariance matrix right now and then figure out what we think it should be when this new observation comes in. So we're going to take a known established covariance matrix and figure out what we think it should be predicted at an observation in the future. Now this is where we're going to do a whole lot of hand waving. All right, there's a little bit more detail in the handout if you're interested, and then of course Velato, I don't know how many pages on this. This is a whole career field. This is mostly, in my opinion, an application class. We're not going to just make up equations and see if you know how to program. You need to kind of have some familiarity, right? But we're not going to spend 4 lessons going through linear algebra. I guess we'll spend at least more than 4, but we're going to try not to focus entirely on that. We really got to get into the applications. So here's where the hand waving comes in. We know that variance itself, I imagine you've seen this before, you're subtracting some prediction data. You're subtracting data and a prediction, or the mean. In this case, it's not the mean, but you got predictions and observations, and you subtract those, square them, sum them all up, divide by how many observations there were, and it's giving you a measure of the scatter around your model. Okay, so fundamentally, variance is a function of the observations and your model predictions. So covariance is a matrix form of that, but I guess we know that it would be a function of that stuff too. So luckily, we have a way of predicting states or state corrections. We just developed that last lesson, and that's a function of psi. So hopefully it makes a little bit of sense that the estimate, the prediction for a covariance matrix in the future is a function of the covariance matrix now, and also that those state matrices. A lot of steps left out there, but that's how it works out, and at least it kind of makes sense that it's a function of the same things. And Q here won't come up a whole lot in this class, but it is the model error. Okay, so in other words, if J3 turned out to be a really big effect, we're not factoring that in. These partial derivatives that we're carrying around in the psi matrix don't factor that in. So there would be some sort of residual error just because our model wasn't that good. All right. So as far as figuring out new update stuff, that completes it. Kind of giving you that last one. And that's it for how to predict the state correction, and the covariance matrix. Now we can do that. So now it's time to go into update mode. Okay, now this is what we did with the sequential batch. We calculated our updated covariance matrix as a function of the last one that was good plus some new data that was contained in the A matrix. Right, we can't use A because it's all partial derivatives with respect to epoch, not now. We want partials of the current prediction with respect to the current state. So we're going to swap out A and call it H. It's going to be very similar, but it's different. Okay, so it's going to be the partial of my model propagated to the new observation with respect to each of its x, y's, and r's and v's. So for example, it'd be a partial of how does azimuth at observation 5 change when r sub y changes at observation 5.
This is how it works.
So how do we find it? We've actually got to be able to find these things to code them up. Turns out it's easier in a lot of ways. Okay, so you've got a partial of all the observations, rho as L, with respect to the 3 R's and the 3 V's. But the partials with respect to velocity will be 0. How does rho change with respect to a change in velocity x? Well, if they're both right now, it doesn't change at all. If one satellite's coming this way, one's coming this way, and they have the same rho as L, a delta V doesn't, it will affect different rhos, but right at that instant it doesn't. If you're propagating from epoch and you give it a big kick in velocity, then the rho as L will be different. But if they're both right now, then it doesn't matter how it's moving. The rho as L is just a function of the x, y, and z. And also, making our life easier, is that we don't have to use cowl every time we do one of those tweaks. And we're not done with cowl. We had to find the current observations prediction, we had to use cowl from some known position and velocity. But once we're there, we don't have to use cal to, when we tweak r sub x, for instance, we don't then have to propagate cal into the future, because we're already at the new observation. And so these are kind of how the partials break down. It's going to be a bunch of zeros for the velocity stuff, and it looks a lot like the A matrix otherwise. All right, so now the equation we've been using, or at least looked at in sequential batch, looks more like this. Does that make sense, Josh?
The only thing holding you back in this life is your discipline. Your discipline is the only thing holding you back.
Okay. So our new state update vector is going to be a function of predicted stuff. This was predicted, and then also the H matrix and the actual error matrix. So this looks a lot like batch sequential, except we've updated everything into time, and we don't say A anymore, we say H. And then the covariance matrix is still this first part, or if you write it separately, it looks like that. All right, so we're in the home stretch. How can we do need to look at one more thing, though.
Yes, this is a massive topic. The amount of capacity towards the endeavors we pursue.
The Kalman gain. Right, so this is the equation for the covariance matrix, which we know we need to keep track of, and this would work. But P is a 6x6 matrix. There's 6 positions, 6 velocities, all these partials, becomes a 6x6. And we're going to have to invert it, do some linear algebra, then invert it again. This is going to bog us down. All right. So what we do is we use the matrix inversion lemma, which tells us that if we have something like this, it can be written like this, where K is this. So why are we doing this? So that we're not double inverting a 6x6. But we are still inverting some stuff here. We've got to invert the W matrix and then do some linear algebra and invert it again. But if we're adding one observation at a time, like we're kind of set up to do here, this weight matrix is just the weight. It's a single number. It's the weight of the new observation. Well, there'll be a rho as an L. But these inversions are pretty much just divisions. Okay, and then similarly, the H matrix is a 3x6. Half of them are zeros, and so this ends up being a 3x3. It goes a lot quicker. Okay, so that is my Kalman gain matrix. We'll calculate that, and then we can do calculations like this. So, in other words, these are the key equations we come up with. Our covariance matrix, including information from the new data, is this. Okay, so it's based on this linear algebra here and the predicted covariance at that same observation. And then the correction we actually need to make, the calculated correction that we really actually want to make, is a function of the old correction plus some linear algebra and what we thought the correction would be before we started using any of the data from the new observation.
We roll like that.
So where does that leave us? Where does that leave us? All right, so I'm gonna actually use numbers instead of K's and N's. Let's say that we are at observation 5 and we've processed everything behind us and it's as good as it's going to get. So in other words, we have a state vector at 5, we have the correction to the state vector to get us there, and we have a covariance matrix at state 5, all finalized, all calculated and done. That's why they have a hat. And then boom, observation 6 rolls in. So we'll go into predict mode. So we use cowl to get from our state at 5 to our predicted state at 6. Doesn't include any new information yet. The predicted state correction, we use that equation. Okay, of course, to get there, we're going to have to calculate psi, which means we're going to have to calculate f. So a couple calculations that you know how to do, but they're getting inserted into your code. And then I need to predict a new covariance. So covariance at 6 is going to be a function of the state transition matrix and the actual covariance at 5 plus that q. All right. Then we go into correction mode. Okay. So to correct, we're going to have, the correction is driven off of the error matrix between what we see and what we expected. So we calculate the b tilde for observation 6 using the observations and the predicted state at 6, which we just got. There's really nothing new there. Then we calculate the updated state correction. Okay, so that is my updated state correction. It includes information from my last good state correction and the error I saw in some of these matrices I've calculated. So to get here, I've got to calculate K and H. Then I calculate the corrected covariance matrix, reusing some of those matrices, and then it's a function of what I thought it would be as well. And then lastly, we can actually update the state vector at observation 6 using the prediction at observation 6 plus the corrected del x hat for observation 6. So, a lot of tough slides there, especially you roll it into the last two slideshows. But as we start to get out of the woods, we don't have to keep all of that in our head at once. We boil it down to what we need to use and move on out. So to really use this, you've got to compute an H matrix, which we just talked about how to do, an F matrix from last lesson, and then use them in a few new equations. And at this point, a lot of the trees fall away, and we just have a few key takeaways. But to really effectively use this, we at least have to know what we're doing and what's going on. Really get our algorithm straight and get down to a lot of careful programming. Okay? So that's where we'll leave it for now. What we have left is to come up with a lesson where we don't have the derivations. We have those key takeaways. And actually think about the order that we do this stuff in. So that'll be up next time, and then you'll be on your way for the EKF project, which will be you'll be modifying your LSDC, developing a few new matrices, a little bit different linear algebra, and taking one observation at a time, and then comparing the results to LSDC. So that's it for today.
And then apply the universal knowledge that's being supplied. You're being supplied the answers when you earn